Yesterday night in the last class we ended by writing down a very important result regarding log barrier functions, and this result is already on the screen as you can see. So, it says that if I take the interiority condition, that is the strict feasible set of the primal problem and the dual problem both are non-empty, then all the rest B, C and D will follow. That is, for whatever mu you take, there would exist a unique minimizer to phi mu. Whatever mu you take, there will be exist a unique minimizer to phi tilde mu, and that system f mu x y is equal to 0 will have a solution. That is, the relaxed KKT or the approximate KKT system will have a solution. So, the unique fact, that the interesting fact that this result tells us that this mu is not a very big problem. You can take any mu strictly bigger than 0. So, that is why we have written here for any mu and for any mu. Okay. Now, this is something very important and we have to keep in mind, because this is central to the development of algorithms for interior point algorithms for linear programming problems. Now, we said that okay, we will try to give a proof of at least a part of the result. So, we will just prove that okay, we will assume that we know that A implies B. So, okay, the interiority condition holds, and so we will try to now show that if I have B, I will have D, and if I have D, I will have B. Now, proving B implies A and A implies B involves certain difficulties which I do not want to put you in. It involves a lot of technical issues, and lot of the viewers here who may or may not be doing any sort of may not be involved in rigorous mathematics, but just really want to know the basic ideas involved in this sort of algorithms, may not be thrilled with such a proof. So, it is very important that you also at the same time have some basic understanding that okay, if I can find a minimizer, a unique minimizer of the strictly convex function phi mu, that is the barrier function, then I am actually solving the inexact KKT condition. So, here we cement a link between the solution of barrier functions and the solution of the KKT system, the approximate KKT system, which will generate what we call the central path in interior point methods. So, phi mu here can be actually, instead of being generated over only f naught p, it can be generated over int Rn plus also. And now, what we know, if we assume B to be true, so we know that this problem has a unique minimizer, because this thing constitutes the feasible set f naught p. So, I can write the feasible set which is actually f naught p here. So, just for sake of it, I am writing it in a simpler way. I am writing it, I am putting f naught p equal to s for the time being, and I am writing it like this, which can be written as the intersection of these two sets. Since x bar is a unique minimizer, then the optimality condition, which is of course this optimality condition is an if and only if condition. Then this optimality condition holds. Then actually we can show that this is equal to this plus this, where this is this, C hat is this. Now, how do we show that? We can write the indicator function of this as a sum of the indicator functions of these two sets, and this indicator function is nothing but, as you see, is 0 when x is in S and plus infinity when x is not in S, and this is what we have discussed earlier, and you know that the subdifferential of the indicator function will give you a normal core and blah blah stuff, and this is applying the subdifferential sum rule. So, sorry, this should be like this, delta of, so subdifferential of this. So, the normal cone to S delta of this, and then the sum rule is applied. If you do not remember how a sum rule is applied, let me tell you that the delta function on Rn plus plus, the domain of the delta function, the convex function is Rn plus plus, and it is continuous on Rn plus plus, and that is why you can actually do the sum rule, you have equality, and then writing down this definition that the subdifferential of a indicator function is a normal cone, you have this. But this being an open set, you can prove that if x bar is element of interior of some set say A, then some convex set A, then normal cone to A at x bar is nothing but the 0 vector. This has, so it is a cone which is a trivial cone which consists just 0. Okay. So, this ns x bar is nothing but nc at x bar, and nc at x bar we have studied earlier is nothing but the image of A transpose. That is, for any v in nc at x bar, there exists y in Rm plus. So, instead of this we should write, so for any v it can be replaced, for whatever v you choose here, give me a v, there would be a y in Rm such that v is equal to A transpose y. So, which means there exists a y in Rm such that this holds, because this is nothing but the grad of phi mu at x bar, and this is finally. So, this is the normal cone element which is of the form A transpose mu. So, instead of taking y, I am taking just I am putting replacing y by minus y, doesn't make much of a difference, just for simplicity. Instead of y, I have just put minus y, it does not matter. You can say there is a minus y in Rm such that this holds. So, if I put S is equal to this, which is exactly, if you look, if x is, where x is the diagonal matrix having these as diagonal elements. Now, this x is in the interior, because x is all these x1s, x2, x3, these are all bigger than 0. So, you can, this definition mu of x inverse, this is completely clearly defined. So, this is nothing but the vector mu x1 dot dot mu xn. So, you are getting S1 x1 equal to mu, Sn Sn equal to mu. So, you are basically solving this system that is required, you are solving the system f mu x s f mu x y s equal to 0, and this is not giving you this, and obviously you have Ax equal to B, because your solution set has to be a feasible point, and also it satisfies this. So, any solution of that actually solves this system, it gives me a y, it gives me a s, which is this, and in fact, the interesting part is that x is created from s is created from the x itself. So, if I know the solution of the barrier function over f naught p, then from that I can create the s, and then the y automatically is generated, and hence I have also got this, and also just by from the definition of s I have got this. So, there is a relaxed KKT, which is relaxed KKT. So, this relaxed KKT is also solved by the same solution. So, B would imply D. Now, if I assume D, that is such an x exists, then I can go back and do the same argument step back, and so I can go and have that this a solution of the relaxed KKT system would imply that it is a unique minimizer of phi mu over f naught p. Phi mu being strictly convex function, the minimizer would be unique. Now, I would leave the reverse argument to you to do as a homework, but remember that this is a very important notion. Now, again I want to recall you that if you look at the very fundamental Newton's equation, then there is an, for each x y s, this is the Jacobian of that system. Now, this Jacobian, of course, f x y s is A transpose y plus s minus c, A x minus b and x s e. So, if you take this is exactly the Jacobian, and this Jacobian is invertible if this and this is greater than 0, and this is very important for us to note. Now, what is the central path? central path is nothing but for different mu's the solution of the approximate KKT condition or the relaxed KKT condition. So, for every you change a mu you have one solution, you change another mu you have another solution. So, it is again I want to remind you, though I have been reminding this for a long time, that you keep on solving this system of equation and all the points that you get they create a path in the feasible space, and that is known as the central path. So, the central path exactly is not really in just the primal feasible space, but of course, it will create a path in the primal feasible space, but C hat, this central path C hat is a subset of the primal dual space. Now, if I take the XS space, that is X into S space, which I should write more as, then if you project the central path on the XS space, then what you have x1 S1 equal to x2 S2 equal to x3 S3 equal to dot dot xn Sn. So, this is exactly what you will have, you will have a straight line in the XS space, and this formalism of projecting the central path into the XS space has very important ramifications when we will study, for example, 3 different types of projection or 3 different types of methods, 3 different types of 2 or 3 different types of path following methods. Now, we will write down an example of computing the central path. You must remember that the central path is very well defined, because once you have defined the interiority condition that there is a strict feasible solution, then immediately we know that whatever mu you take, the f mu x y s equal to 0 has a solution, and each of these solutions correspond to a path in the a point in the central path. So, you are taking the primal problem LP, so I have to minimize this function in 3 variables. Of course, x is bigger than 0, basically this means x1 bigger than 0, x2 bigger than 0, x3 bigger than 0. So, for this problem I would like to find the central path. So, I would now write the dual problem dp, not really the dual, but the extended dual or the equivalent dual. So, how do I do that? I would leave this again as a homework for you to find the dual, but the dual in this case there is only one constraint. So, one equality constraint. So, number of dual variables equals the number of equality constraints. So, we will have max of y subject to A transpose y plus S equal to C. So, there will be 3 such equations plus 3 such C's here. Here what is my A? A is just 1 1 1 and you have x1 x2 x3. So, it is basically the vector 1 1 1. So, it is a 1 cross 3 matrix. So, A transpose is 3 cross 1, it is the column matrix 1 1 1. So, 1 1 1 into y. So, it is y y y. So, A transpose y is just y y y and you are adding S to it, which is S1 S2 S3. So, this equal to C subject to S1 S2 S3 bigger than 0. Now, once you know that, now my KKT condition, what is my KKT condition? What, let me write down the relaxed KKT. Relaxed KKT is this system y plus S3 plus 4 equal to 0, x1 S1 equal to mu, x2 S2 equal to mu, x3 S3 equal to mu. This is my relaxed KKT. Of course, xi Si is strictly bigger than 0 because mu is strictly bigger than 0, xi is strictly bigger than 0 and Si is strictly bigger than 0 for I equal to 1, 2, 3. Now, what you have from here, let us take the calculation here. So, what do I have from this system? I would have S1 is equal to minus 1 minus y1, S2 is equal to minus 3 minus y2, S3 is equal to minus 4 minus y3. No, sorry, I am making a very bad mistake. Y is same. There is only one y. This is what you have. So, all of these would imply that y is strictly less than minus 4. Now, from this set of equations x1 S1 equal to mu, x2 S2 equal to mu and x3 S3 equal to mu, I will get the following expression. So, 1 by mu is 1 is x1 plus x2 plus x3 by mu, because this is equal to 1, and then this will become 1 by S1 plus 1 by S2 using this set of equations, the last one, this set of equations. And this now you can put, so mu is now, there is a relation between mu and y. So, I can express y in terms of mu, you see, once I express y in terms of mu, I can express s in terms of mu, and hence I can express s in x in terms of mu. But what is s mu is equal to 1 by x mu, that is all, a mu by x mu. So, mu is actually given to me. So, this is it is the cubic equation that you will have. So, you can solve the cubic equation by the usual Cardano's method or some other standard algebraic method. You solve the cubic equation, and solving we have a solution y tilde, which is a solution of this equation, y is expressed in terms of mu. Now, once I have this, no matter what, I will know that once I have y mu, y tilde mu, I will have s tilde mu. When I have s tilde s mu basically. So, when I have s mu, I will immediately have x mu. So, that will keep on generating the central path as I change mu. So, this is one simple example that even for a very simple case, how difficult it could be to find the central path. So, the question is it advisable to really make an attempt to do such things? The answer is of course not. You do not attempt to do such things, because these things are so complicated for very such simple problems. It would be so complex if the problem is very large. So, what we are supposed to do then, that is the question. So, we have to go to the basic structure of the primal dual framework. Okay, we will now go to the basic structure of a primal dual framework. basic structure of a now, once I am talking about the basic structure of a primal dual framework, what we would have is the following, is that we cannot now attempt to think about finding the central path. So, what we have to do? We have to do certain slight modification in our Newton system, so that we attempt to find points which we solve that new slightly modified system approximately, and so we try to find certain points near the central path, and we have to show that it is enough to find such points. We do not need to find some extra something much more rigorous. These sort of approximate points will finally lead me to the solution, and that is exactly what you want. So, in general, given any x, y and s, I do not know whether they are actually primal feasible or dual feasible. So, in general, x, y, s is given, which may or may not be feasible. So, if it is feasible, then it is fine, if it is not feasible, okay. So, let us do the standard thing, writing x k plus 1 y k plus 1 minus y k is delta y k. This is a standard sort of notations. Some books obviously make a little change, they write this as minus grad x, does not matter, just to adjust the minus in the Newtonian sign. Now, let us write down this system. Unless they are feasible, we do not know whether this is 0. So, we can put this dual residual, that is, it is not 0, but something else. So, we define it basically. The primal residual and the complementary residual. Excess mu is R C. So, our Newton's equation is of this form in general. Or the Newton scheme rather, I should say. If you are little bit of more erudite, you will say it is a Newton scheme. In this particular case, it will look as this into delta, instead of k I am writing k here, delta x k, delta y k, I am just writing delta x. Delta x means x k to x k plus 1 for the time. Of course, you can write delta x k and find for every k what is it, but does not matter, it will be almost the same, it will depend on the x at that moment, x k at that moment. So, I am, or you can say okay, I write delta x to denote x plus and x. In general, this would mean k plus 1, this will mean k, that is all, I mean x k plus 1 minus x k. So, do not bother, you can put x k also, does not matter, I am just for simplification I am writing it in this form. this is exactly my Newton scheme, but if all are 0, these two are 0, then 0 0 minus RC. Okay. Now, can this equation, system of equations, have a solution? Okay. I can slightly modify this equation. Now, because x and s is strictly bigger than 0, because when we start our basic structuring, an assumption which is standard is that the interiority point condition hold. So, now what I will do, I can do a little bit of restructuring. So, I will multiply this row, block row, by S inverse. So, what you will have here is, so if I multiply S inverse, it will remain the same, it will, the new solution, new system will give the same solution. X by S basically. Now, can I actually solve them out explicitly? Can we this is equivalent, I am not writing, we can we explicitly compute delta x, delta y and delta s. So, we take this and go back and try to do this one. So, now what we are going to show, as we have said, that can we solve out this delta x, delta y, delta s. Now, the question is very simple, that by solving this we are solving the Newton system for this particular, for the inexact or relaxed KKT system, and that is what we need to solve to find the central path. So, this is very important that in our algorithms or the program that we will write, we will have to know the solutions of this. So, our first step is to know that can we solve the Newton method explicitly. So, it will be easy to program it, because solving the Newton step would become expensive because of the inversion that you would require of this matrix if you can't solve them explicitly. But though you will need some inversion, but it is very good to store the inverse at the very beginning, because these matrices are fixed, and so then you can immediately write down the whole thing. So, instead of writing inverse of matrices, doing the inverse of this whole matrix or this matrix A or whatever, what we would like to do is, without using the inverse of this whole matrix or without using the inverse of this A or A transpose whatever, we can simply compute this delta x, delta y, delta s, in only inverting the diagonal matrices, which are just simple things. So, now we will write down the whole system once again, which is so we will do the step by step computation now. This is equal to minus of RC, sorry, RD RPRC. So, let me see. So, what do I get from this? I get A transpose delta x, sorry, delta y, not delta x has nothing to do, is with 0, A transpose delta y plus delta s, I into delta s is delta s, is minus RD. A times delta x remaining at 0 is minus RP. S times delta x plus x times delta s, the last one, give me minus RC. Look at the first one. From the first one I would have delta s is minus R D minus A transpose delta y. Now, from the last one what I will get, forget about this one. Now, for the last one I will get S inverse minus R C minus x delta S. So, what was R C? R C was, just again reminding you, R C was x s mu e. X s minus mu e. So, what would be done? X and s would commute, these are diagonal matrices, and so you will have minus x plus S inverse of mu would come out and S inverse of E. So, it will become S1 S2 S3. So, mu 1 S1 mu 1 S2 mu. So, or you can just write mu S inverse E minus x S inverse x and S, they will commute as diagonal matrices delta S. So, this is what is delta x I have got, right. Now, I will substitute these delta x into this equation. So, I will get delta S from there. So, putting delta x in the second equation, so let us put delta x into the second equation. So, A times minus x plus mu S inverse E minus x inverse delta S is equal to minus R P. Now, once I know this fact, I can immediately write down. So, x here means x k. So, instead of writing this, you can also write the second equation as A S inverse minus R C minus x delta S is equal to minus of R P. So, you will have A S inverse R C minus A S inverse x delta S is equal to minus R P. Now, delta S you know from here, there is something. So, you can write A S inverse R C minus A S inverse x into delta S is minus R D minus A transpose delta y. This will give you minus R P. Now, A S inverse R C minus A S inverse x minus minus plus R D minus minus again plus A S inverse x A transpose delta y is equal to minus R P. So, A S inverse x A transpose delta y is equal to minus R P minus A S inverse R C minus A S inverse x R D, and delta y thus is equal to A S inverse x A transpose this into inverse of this part into minus R p minus A s inverse R c minus A s inverse R d. So, this is delta y. Now, you must ask me why are you suddenly inverting this? Let us see why we are suddenly inverting this. Minus A s inverse x A transpose R p plus A s inverse R c minus A s inverse x R d, A s inverse x R d. Now, why this inversion is done here? Because this matrix is positive definite. Now, how do you prove that this is positive definite? So, very important thing to note here, A x S inverse A transpose is positive definite. Let us see what happens with x A x S inverse A transpose x. So, this would imply this would be equal to some x in as per the symbol. So, if we take the inner product, how would you say that this A is full rank? So, how do you take care of x s inverse? That is the whole thing. So, this matrix is nothing but x 1 s 1 x 2 x 2 x n s n. This has to come with this one. Now, the positive definiteness of this part is an important issue here, and how would you prove this positive definiteness is something one has to think about a little bit. Note that this is positive definite. So, it is not so simple to figure out that this is positive definite, it takes a little bit of time. So, I ask you to go and do it as homework. So, once you know delta y, you can figure out what is delta s, because once you know delta y, you know delta s is nothing but minus R d minus A transpose delta y, and once you know delta s, you know delta x. So, this can be also taken as homework, but it will be very important to know that whether this matrix is having whether this matrix can be and how to prove that this is positive definite. It is slightly an important thing. You have to know that there is something called a square root of a matrix, and you can express this as for any positive definite matrix there exists another matrix B, positive semi definite matrix there exists another matrix B such that B square is equal to A. So, if A is a positive semi definite matrix, then there exists another positive semi definite matrix B such that B square is equal to A. So, try to write this as, so that is called the square root. So, this is usually given by half. Try to write this as this and then try to solve this problem. This is anyway a symmetric matrix. So, do not worry about it. So, with this with this little homework at the end, we end this thing, and the next class we will start the central framework of primal dual methods, IP interior point methods. See, our standing assumption would be that there is absolutely no question that the interior point condition is holding, that is always there. Thank you.